This video we're going to be talking about power functions with rational exponents. Again, power functions with rational exponents represent radical functions. Now let's remind you how to change from the exponential form to a radical form. X to the m over n power, reminder, would be written as the mth root, and that would be f of x still. F of x equals the nth root, of x to the m power. So the bottom number is the index on your radical. The top number is an exponent. When n is even, such as if you have a square root, a fourth root, or a sixth root, the domain will be restricted to only positive values. You cannot take the square root of a negative. You can't take the fourth root of a negative. So again, examples. Number one, we're asked to graph these and identify its key characteristics. Since it is a fourth root, again, this is the fourth root of x to the first power. Since it is a fourth root, remember that you can only find the fourth root of positive. So therefore, there will be nothing to the left of your y-axis for this graph. Okay, I plugged in some points, plugged in 0, got 0, plugged in 1, got 1, plugged in 16. You might be saying, why'd you jump from 1 to 16? I only plugged in values that I know the fourth root of. You can plug in 2, 3, 4, and it's going to give you like 1 point something. But the reason I plugged in these whole values because, again, that's the ones I know the fourth root of, so that's really all you need. Domain of this function, 0 to infinity. The range is also going to be 0 to infinity. Now, it looks like there's an asymptote line here. It is not. This thing continues increasing over the term of the entire 0 to infinity. The x-intercept and the y-intercept is going to be the origin here. Increasing interval, this thing increases from 0 forever. So that would be from 0 to infinity. Decreasing, it does not have any intervals where it's decreasing. Symmetry, there is no symmetry here. Discontinuities, and that would be either whole, infinite, or removable. There are no discontinuities. End behavior. And notice the end behavior I've written a little bit different. It says as x approaches infinity or as x approaches 0 because we're not going to negative infinity at the other end. We're actually just going to 0. So as we travel to the right, your y value goes up forever. As we go to the left, my y value actually goes to 0. Second one, 1/2 x to the 1/5 power is the same thing as 1/2 times the fifth root of x. And we can take the fifth root of negative values. Let's make us a table of values and plot us some points. Okay, so there's your points. Plug in 0, get 0. Plug in 1 and -1, give you 1/2 and -1/2. Now, I did plug in 8 and -8 here to give us another point on a graph, just to show you that you can plug in those numbers you don't know the fifth root of, but you are going to get decimal values for those. My domain and range. Domain is everywhere, and range is also going to be everywhere. Now, it does not look like it from this graph, but you could set this y value equal to anything you want to. You can set it equal to 10, you can set it equal to 100, and you can actually solve that. Multiply by 2, raise it to the fifth power, and you're going to get a y value. So there's no range restrictions here. It's just going to take a while to get to 100 on this graph. Your y-intercept and your x-intercept are both the origin for this power function. Your increasing interval, this actually increases the entire length of this function. It's constantly increasing or going uphill. It decreases nowhere. Now this one does have some symmetry. This does have origin or rotational symmetry. Discontinuities, there are none. And end behavior. Okay, as we travel to the right on our graph, y goes up forever. Now it goes up slowly, but it does go up forever. And as we travel to the left, y travels down forever. Okay, on to the next problem, number 3. We're graphing now negative 3x to the 5/2 power. First thing you need to do is rewrite it. That'd be negative 3 times the square root, or the bottom number is the root, the second root of x to the 5th power. Now let's do a t-table and plug some values in. And here you see a look at the graph now. I want to point something out. This is a radical function, so it has the basic shape of all radical functions. However, this one grows so quickly because it's being raised to the 5th power. That's the reason it looks the way that it does. So it does have that same shape. It's just flipped over and grows extremely quickly. The domain would be, it starts at 0 because it does not include negatives. You can't find the square root of a negative. The range value here would be from 0, or excuse me, we start at the bottom, from negative infinity up to 0. The x and y intercept are both going to be at 0, 0. Increasing interval, it does not increase anywhere. However, it does decrease starting at 0, and it decreases forever. Symmetry, there is none. Discontinuities, there are none. And finally, in behavior, as we travel to the right on our graph, your y value decreases because of the negative out front. As we travel closer to 0 to the left, my y value gets closer to 0. Okay, example number 4. These are examples in radical form. And just a reminder that if it's in radical form, that you could change it back to exponential form if you need to type it into a calculator or something like that. The number on the index would be the bottom number of your rational exponent. The top number would be the exponent that's on the x. So this is negative x to the 2/3 power is what we're actually graphing here. Plugging in some values, we're going to get a different looking graph, pretty neat looking graph here. We plug these values in. Let's do a t-table over here. And here's what I get. Now, notice that I plugged in, along with 1 and negative 1 and 0, I plugged in 8 and negative 8. And the reason I did that was because, again, since I was taking a third root, and remember that you can take a third root before you square. So I was taking a third root. I knew that the third root of 8 was 2. Third root of negative 8 was negative 2. So that was going to be pretty easy to graph. So you get this odd shape looking square root graph here. The domain is going to be all real numbers. The range, however, is going to be all values from negative infinity up to just 0. It's not going to go any higher than 0, so that's your upper bound there. Your x-intercept and your y-intercept are going to be the origin. Increasing interval, it increases from negative infinity up to 0, and then it starts decreasing, going downhill. Symmetry, this actually has y-axis symmetry. So therefore, this would be, I'm going to put in parentheses, this would be an even function. Discontinuities, there are none in behavior. As we travel to the right on our graph, our y value goes downhill to infinity. As we travel to the left, our y value also goes downhill. And number 5. Here's the graph that we're asked to graph. Now, it's going to be hard to be picky about what we plug in here. I see that 1 is probably going to give us fits, 2 is going to give us fits, 0 would be easy to plug in. But let's just pick some values, and we might have to use our calculator to get some decimal approximations. Okay, so here's my points that I plugged in 0, 2, and 3, and then I notice, hey, I can plug in negative values here as well. Biggest thing you need to make sure of, when you're plugging in a negative value, you have to raise it to the 3rd power first before you subtract. So that's how, when I plugged in negative 1, I did negative 1 to the 3rd, which is negative 1. 27 minus negative 1 would be the square root of 28. And I did my decimal approximations, and here's the graph that I got. Notice you can't plug in anything to the right of 3, because then you have the square root of a negative. Or you can think of it like this. The stuff under the square root symbol has to be greater than or equal to 0. When you solve that inequality, you're going to get that x has to be less than 3. So therefore, my domain is all values from negative infinity up to that 3, and 3 is included. I can find the cube root of 0. The range of my graph, notice that I will always get values above 0 and above. My x-intercept, I do have x-intercepts here. My x-intercept is located at 3, 0, My y-intercept is located at 0, comma, I believe that was 5.2, or you can put 0 root 27. Increasing interval, it never increases, it's constantly decreasing, and it decreases from negative infinity up to the end of the graph, which is located at 3. And again, that's always x values. It has no symmetry, it has no discontinuity and end behaviors. And we'll do as x approaches negative infinity first. So as you go to the left on your graph, your y goes up forever. And then as you approach 3, that's the other end of your graph. As you approach 3, your y value approaches 0.